For the past 27 years. Whoa. Back when I was a real young guy, and he was.
I was pretty old.
And he had more hair. Wendell has just retired from NASA after 50 years of service. And among his many accomplishments are serving as principal investigator of an Apollo 17 experiment back in 1972, and writing the first real critical book on lunar bases in 1985, called Lunar Bases in the 21st Century. And he has been a strong advocate of getting people off this planet and somewhere else for his entire career. And so let's give a warm welcome to Dr. Wendell Mendell.
Thank you very much, John. When I was invited to give the Jerry Soffen Memorial Lecture at this year's International Space University summer session, I was both honored and amused. Jerry and I had some interactions always through ISU, and I thought I would tell you a little bit about what I remember about working with Jerry. As John said, Jerry was the project scientist for the Viking mission, which was a really important position. The data from the Viking spacecraft, we spent a year or more on Mars each, really defined what we thought we knew about Mars, and particularly about the possibility of life on Mars. One of the major findings from Viking was that they could not detect any carbon at all in the soil of Mars, and so for at least 2 decades there was a conviction that there just couldn't possibly be life on Mars. And that began to change, first with the work on the Martian meteorite, where there were thought to be biomarkers found in the Martian meteorite, which is a very controversial paper. And now, of course, there is a whole armada of robotic spacecraft on the surface that are discovering all kinds of evidence for water on the surface and so on. We'll talk just a little bit more about that on Thursday morning with the Moon and Mars lecture. But Jerry was a very important senior scientist. He was a biologist. At the time, I was a junior researcher working on the Moon at the Johnson Space Center. So our paths would never have crossed, except for the fact that we both got interested in ISU. I became heavily involved in the very first session. Jerry became involved later. He had a very great passion for education, and in fact created an entity called the NASA Academy inside NASA that was to some extent modeled on the success that ISU had experienced in its lifetime. But I have 2 specific memories of Jerry. The first one, I can't remember the year. It must have been early in ISU. I can't remember what country we were in, but I do remember the table we were sitting around. Jerry was at the front of the table. There were ISU faculty around the table, and Jerry had recruited us to do some brainstorming about a subject in biology, possibly about teaching biology or getting biology into the space program. And I'm not a biologist, but I think I'm a pretty smart guy, so I ought to be able to contribute something to a discussion like that. And at one point there was a topic raised, and I had just read something in a magazine or in the literature, and I thought, there's an interesting connection there. So I raised the point, and Jerry stopped the meeting and turned and looked at me. I was about 2 chairs away from him, and he said, "Wendell, that is the most stupid thing I have ever heard." There were a number of seconds of awkward silence in the room, and the meeting continued, and my further contributions were minimal. In 1991, in the 4th ISU summer session, I was the design project director. Now, in 1988, there was one design project for all of the students. The 1988 session was the initial session where everything was chaotic. The topic was a human lunar base that would start out as a research station and evolve over 30 years into a fully self-sufficient commercial entity. It was a massive project, and all of 100 students, and we got our way through it. And the next year I was asked to be a design project director again, and I declined, partly because I liked the idea of one design project for the whole class, and there was going to be 2 projects, and partly because the topics of the projects weren't part of my expertise. But for the next 2 years, 89 in Strasbourg and 90 in Toronto at York University, I watched the design projects, and I saw certain tensions among the students. I saw certain dynamics that occurred, and I made notes. And in 1991, the ISU session was to be held in Moscow, hosted by the Moscow Aviation Institute. And Todd and Peter, the ISU founders, were just absolutely ecstatic. They saw the Soviet Union as the birthplace of space with the heritage of Tsiolkovsky, and they felt that once they got in well with the Soviet bureaucracy, there was going to be a stream of money. And so there was this great excitement about going to Moscow. And they were going to have one design project for the entire class, which would be a human piloted mission to Mars, which was, of course, on the Russian agenda at the time, the Soviet agenda. And Viktor Legostayev was going to be my co-director, one of the legendary engineers in the Soviet space program. I had never met Viktor. He'd never been involved with the ISU before, so I wasn't quite sure what to expect. Well, in the planning sessions, that was the year the Soviet Union collapsed. And about December, ISU heard that from the Moscow Aviation Institute that they weren't sure they would be able to provide security for the students, much less food. And so they just had to back out. And the aerospace community in Toulouse, France, through a Herculean effort, put together facilities and residences in short order and hosted this session in 1991. There were 135 students that signed up because they all thought they were going to Moscow. And there was going to be one design project, so I was in charge of 135 students, and I had some fairly radical ideas about how to run the design project based on what I'd observed the previous 2 years. So Viktor Legostayev hadn't shown up, I hadn't heard from him. So I'm in my office the day before the session is going to begin. I'm looking through my papers and getting them organized, ready to make the presentations. And Jerry Soffen appears in my door. And he says, "Wendell, tell me about the design project." So I walked through what I planned, worked through the processes, why I was doing things, explained everything to him. He listened attentively. And he looked at me and he said, "That will never work." And he walked away. So you can imagine that since those were my memories of my interactions, that how I was interested in being the Soffen Memorial Lecturer. Jerry was actually a pretty nice person, but he did not suffer fools. And he was very blunt in the way he dealt with people, but he had a great passion for education and contributed a lot to ISU, and that's part of the reason there's a memorial lecture for him. But when I was invited to give the lecture, I was asked to talk about something, tended to title the moon, past, present, and future. wasn't quite sure what that meant because I spent decades working, as John said, on the idea of human exploration of the solar system beyond the Earth, starting with a human lunar base. And I thought about possibly resurrecting some of those things, but after the cancellation of the lunar program in 2008 in NASA, it seemed like it was going to, if you bring up the old stuff, what's the point? So I thought that perhaps today I would take your time and spend a few minutes talking about the moon and its importance in planetary science, because I am a planetary scientist, and the President of the United States said a few years ago about the projects to go to the moon, been there, done that, and I'm sure that he was told that by his technical and scientific advisors. But that's a lot. There are a great many people who think, well, we've been to the moon, let's go someplace else. Of course, that's fairly silly because the moon is actually a fairly complicated place. But not only that, the moon has a great deal of information associated with it that tells us about other things in the solar system and how to interpret the data that we gather through our spacecraft as planets like Mars and Mercury, Venus, the satellites of Jupiter, and so on. So the title of my lecture today is The Moon as a Rosetta Stone for the Solar System, implying that by what we studied on the moon, we developed certain ideas of how to think about other planets. This is a slide that might be put up by Neil deGrasse Tyson of the 8 planets of the solar system. And from this slide, it's pretty clear that there are 2 kinds. The ones on the left are fairly small, and the ones on the right are really big. And people who study the planets tended to be people whose specialties matched the phenomena seen on the planets. So the big ones on the right, a person who studied them would be an atmospheric physicist, atmospheric chemist, thermodynamicist, gases under high pressures, possibly winds and storms and computational fluid dynamics and so on. The ones on the left we call the terrestrial planets. And the people who study the terrestrial planets tend to come from geoscience backgrounds, earth science departments, and so on. So they have names like geologists, geochemists, geophysicists, mineralogists, petrologists, and so on, tend to be thinking about silicate rocks. And if you notice that there are 4 terrestrial planets, but I stuck a 5th one in, sort of photobombed the inner solar system. And the reason for that is that the moon, from the point of view of a planetary scientist, one who deals in the terrestrial planets, the moon is actually a planetary body in the sense that the processes that we see on the moon are the same kind of geological processes that we see on the Earth and on Mars and on the other planets of the inner solar system. And the interesting thing about the moon is that we've actually landed there with human beings, and we've collected samples which have been brought back to laboratories on the Earth, and by the way, have been preserved very religiously, and I use that word in a technical term, by the curation staff of the Johnson Space Center and the Lunar Sample Environment. In fact, they're responsible for all extraterrestrial samples and have everything from lunar samples to Stardust to Hayabusa, and various other spacecraft missions that have sampled various bodies in the solar system. And the samples are kept in very strict environments so that they don't lose their scientific integrity, and are still being studied 40 years later, and new facts are emerging from the study of those samples. So it's really important that we have them and that we looked at them. And what I'm going to talk to you about in subsequent slides are a few of the things that we didn't know at the time we went to the moon, and that we now understand much better or more thoroughly after the research has been done on the sample collection. One of the things that we now know is that all of the terrestrial planets are differentiated. That's a big word that means they have been separated into layers, and if you've studied the Earth, you know we have the crust and the mantle and the core, which is made out of iron. but this turns out to be true for all the bodies, including the moon. And the reason that it occurs is because all of these bodies, very early in their career, got incredibly heated, and then the heat caused the bodies to essentially melt, and from the slush or the magma that was created, the crystallization of various minerals as the temperature cools has a certain sequence. They segregate themselves by density, and you end up with this sort of internal, in this picture, spherically symmetric structure. And the moon exhibits this, but there's a really interesting thing about the moon. This is just the moon's smaller picture, in case you didn't know that. I always remember the Mad Magazine quote when I was a kid. I used to read Mad Magazine. Maybe you've never heard of it before. But there was a character called Alfred E. Newman, and he was quoted as that although the moon is 1/49th the size of the Earth, it is further away. So I always love that. It's sort of Zen-like to think about it. The question before we went to the moon, when all we knew about it was looking at telescopes, was was the moon ever hot, or is it just cold? And in fact, the Nobel Prize winner Harold Urey was absolutely convinced that when we got to the moon, we would find a rubble pile, and there would just be stacks of primitive bodies that had been in the early solar system, and we'd be able to look at those and immediately kind of do archaeology about what the early solar system was like. But if the moon had melted, then his ideas wouldn't have worked. And there were other people who looked at these pictures of the moon. You see on the left-hand side, the near side of the moon, the side facing the Earth, has these dark areas that we call Maria from the old astronomical beliefs that they might be seas or oceans. And the geologists who believed in a hot melted moon thought that they might be basaltic lavas of the kind that we find on the Earth in volcanic eruptions and the ocean spreading zones. So the two ideas were that the moon is a primitive object, and that it's pretty much spherical and so on, and that we knew there were mass concentrations under the surface from the lumps in the gravity field, and the fact that they were there probably meant that they were just kind of things bunched up together. The other idea was the moon had been wholly or partially melted, and that these dark areas were basaltic. And in fact, when the Surveyor spacecraft landed and began to do the very first sort of primitive chemical analysis, the alpha backscattering instrument, they showed minerals, chemicals consistent with mineralogy that was like a lunar basalt, with some differences, particularly in the more volatile elements. And in fact, the surface morphology kind of looked volcanic to geologists. And one of the dangers, by the way, in planetary science, particularly in the terrestrial planets, is that the intuition of the scientists is developed on Earth. And a lot of it has to do with their ideas of what things ought to look like. So if they see something on another planet that looks like something they're familiar with on Earth, their first idea is it's the same thing. And this has been incorrect more than once. So the questions were, what is the lunar composition? And does it change from place to place, or is it just homogeneous everywhere? And then there were these things that you see on the right called sinuous rills that look like they might be riverbeds of some kind, and so was there actually water on the surface? The moon has no atmosphere, and the gravitational attraction is just too weak to hold gases, but could there have been some really early era where water could have existed, and maybe some kind of atmosphere might have existed around the moon? And in fact, oddly enough, we are making the same speculations about Mars, although we have a lot better evidence of possible water on Mars now with the rovers and the chemical analysis than we did at the moon, because here it's nothing but a morphological argument that looks like, well, maybe it looks like a river. And the other question was, how old are the features we see on the lunar surface today? And what are these round things? Are they craters or are they volcanoes? I still remember watching a television program the night they launched Apollo 11, where two scientists had an intensive debate over whether these structures on the moon were volcanoes or whether they were craters, impact craters. And part of the problem was that in the 50s and 60s, there was just no belief in the geological community that there was such a thing as impacts. They just didn't exist. If you found a round feature, such as Manicouagan Lake in Canada, it must have been the remnant of an ancient volcano because it was round and it would have sunk in. We now know, of course, that Manicouagan is a very large impact feature, and in fact, some of my colleagues about 40 years ago from the Johnson Space Center spent several field seasons there collecting evidence to show the impact feature. There was a large number of scientific papers written about that. But the very first person to try to convince his fellow geologists that impacts really existed was Gene Shoemaker, who is one of the giants of planetary geology, and particularly lunar geology. And he studied what was called the Barringer crater in Arizona. Now it's known as Meteor Crater, but at the time the crater was assumed to be some kind of volcanic structure. And it was Gene Shoemaker who looked at the rocks in the crater and around the crater and showed that there were shock features in the rocks that could not have come from volcanic eruptions, had to be part of a very high intensity impact that had shock waves that changed the minerals inside the rocks. And he wrote papers about that and was the first person to really champion the idea that on the Earth we had been hit by other things. It was just something that people had never really considered. Now, when we got to the moon, one of the questions was, how old are the features? In fact, this slide's a little out of place, so I'm going to go to the next one. When we brought the samples to the labs on the Earth, we could do very sophisticated analyses of the radioactive elements and their daughter products in certain mineral separates inside the rocks. So these little histograms here, plug in, okay. It says I'm running out of power. Yeah. As soon as we find a plug, but I will tell you what you will see. In front, there's a plug in front.
Front of the stage.
No, in front of the stage.
These little histograms show the dates of different rocks that have been found on the lunar surface. Sorry, wasn't me. And when the slide comes back on, the thing I want to bring your attention to is the axis of ages at the very bottom of the two graphs. And the ages are in billions of years. And hopefully from Jim Green's, well, he actually hasn't given a lecture on the solar system yet. The solar system, we know from these radioactive dating processes, is about 4.5 billion years old. So when we look at the dates on the lunar samples, we're going to see that all of them are older than about 2.8, and most of them are around 3.3, 2.8 billion years old. And that means that the craters that we saw on the surface of the moon are truly ancient. They date back to the very earliest days of the solar system. And those days are totally missing on the Earth because the Earth is an active planet. It has plate tectonics, it has volcanism, it has weathering, it has a biosphere, and all of these things conspire to change the rocks on the Earth, to subduct them into the interior. So it is very difficult to find truly ancient rocks on the Earth. And on the moon, we find that the rocks give us a window into the history of the solar system that is totally missing on the Earth. And that was very exciting. Here's a scale that talks about the geologic ages on the Earth. if you go to a geology textbook, you'll see something like this. And those of you who have looked at such things know that there are all these names for different, that correspond to different strata in the geologic record. They tend to correspond to extinctions and the fossils that are found in different areas, which indicate different changes in the biosphere. But what I want you to notice is that all of the geologic ages that have been cataloged through the history of geology only go back to about 500 million years. So if the solar system is 4.5 billion and the geologic record of the Earth only goes back 500 million, there is a huge missing section that have been kind of given general names with wide spans of ages. And this is just another way of showing the same data. This is the beginning. This is where we are now, and here's all of the geologic, here's all of the named geologic strata, and you see all of this that is basically missing, and here's where the youngest lunar rocks sit. So on the moon, we see what was going on in the solar system from that date onwards, and that was just incredibly exciting. And so the other thing that you see about the moon is that it's really heavily cratered. Now that we have dates, we only have a few dates from certain Apollo sites, but we're able to correlate these with different features on the moon, and so we can say something about the exact timeline. And this graph on the right here shows the dates of the rocks, and notice the ages here: 4.5 billion, 3 billion, 2 billion, and all of this data is here, and then suddenly there's kind of, it goes straight, and there's a really young date here that's uncertain, and here's where the terrestrial record comes into play. And what we found was that by counting the number of craters per unit area on the moon, we could show that different parts of the moon had different ages. You could say area A is older than area B or younger than area C, just from counting the craters. And this crater counting then became a really important way to estimate the ages of surfaces that had this old character. And by golly, when we went to other planets, let me see. So one of the discoveries in looking at the rocks in their age date was that they could not find rocks that represented impacts much older than about 3.8 billion years. And in fact, there seemed to have been something happen that kind of erased the history. And there was a speculation in the early days in the 70s that there had been what was called a cataclysm occur on the moon, where there were a huge number of bodies that bombarded the moon, formed the great basins on the moon, and erased all previous history of the moon. Well, the interesting thing is that the moon and the Earth, as you know, are intimately connected. Any kind of swarm of bodies that came and hit the moon would have also hit the Earth. And so, presumably, the record of the Earth would have been dramatically changed, and if life had existed in some early way, maybe everything had been reset. And so it was really important trying to understand whether there was really a cataclysm or whether there was some other way that this curve fell off that didn't represent a huge spike. And that is still under investigation today. And we're beginning to, and the other question was, where did these bodies come from? Because we're talking about an age that's 500 million years after the, quote, formation of the solar system. And the standard model said that when the solar system was, quote, formed, there it was, and it's kind of just stayed there from then until now. But clearly something really important happened 500 million years after the, quote, formation of the solar system and the removal of the solar nebula and all of the exciting things that happened in the early ages. And where did these things come from? There were thoughts that they might come from the orbits of Neptune and so on. Today, we're beginning to zero in on what actually happened. And Bill Botke at Cornell was one of the people whose work I really love in this area. And we have discovered in the late 90s that the solar system, when it was formed, didn't look exactly like we see it today. And in fact, Jupiter and Saturn and the outer planets actually migrated and changed places through some gravitational interactions. And when they did that, their gravitational influence changed the inner solar system, and they began affecting the unformed planetesimals in the asteroid belt. And it's now fairly clear that this swarm of bodies came from the asteroid belt and pelted the inner solar system. So when we look at Mars and see this heavily cratered surface, or we look at Mercury and see this heavily cratered surface, we make the assumption that they experienced the same bombardment as the moon did, and we can take the age dating from the moon curve, and with some adjustment for the fact that the velocities of the bodies and their flux and so on would be different at different distances from the sun, come up with estimates for the ages of events on these planets in that older terrain. And that's the basis of the ages you see when people tell you that something happened on Mars at some particular age. There's actually a huge amount of uncertainty in that, and we don't really know how to pin down the curve, and that's why we're looking very hard to have samples returned from Mars. We hope in the future that will be possible, because then we can start to pin down the ages of some of these events on Mars and make the right adjustments to understand the ages throughout the entire solar system. Now, one of the things that everybody notices about the moon is that the front side looks really different from the back side. And in particular, there are these mare, these filled basins. We now know that there are basins on the other side of the moon, the large basins, but they are not filled with lava as are the front side basins. Exactly why this happens is still a bit of a mystery, but we all think that it has something to do with the fact that the moon and the Earth have tidal interactions, and that one face of the moon always faces the same side of the Earth. And that very early in its history, the moon was closer to the Earth, tidal interactions were stronger, and we think this dichotomy represents some fossil record of when the moon was sort of frozen and stopped its volcanic activity. Because one of the differences between the moon and the other planets is that its heat engine died very early. Certain kinds of activity occurred, particularly the mare, volcanic flows, but it didn't just stop. And so it represents its early age. This is the Mars dichotomy. You notice that the top part of the figure, this is of course across the sphere, but it's laid out in a cylindrical projection, is very smooth and low. These are altitudes on this. But you notice that the southern highlands are heavily cratered. And that's where we get the idea that Mars was also hit by the swarm of bodies that hit the moon. But then some later event erased everything in the northern hemisphere and had all of these smooth flows. But we don't know exactly what the nature of that event was that caused this huge dichotomy. We also see similar dichotomies on Mercury. Now, the Luis Alvarez discovery of the iridium layer at the Cretaceous-Tertiary boundary that's associated with the extinction of the dinosaurs was the first kind of wake-up call that said these impacts, which nobody believed happened, not only did happen, but actually had very significant effects on the evolution and history of life. And so when you look in the lunar curve, the question is, can you see dates that represent different possible swarms or small swarms of bodies that hit the moon that might be associated with the impacts on the Earth? We can't look at the lunar samples and see those because they're not complete enough. But we now have lunar meteorites that we find on the Earth. We don't know where they came from on the moon, although we can start to make some guesses based on their mineralogy. But we can start to see dates, radioactive dates in those meteorites that begin to fill in blanks in the curve as to whether there were significant events at some time more recent than the formation of the Great Basins on the moon. Now, when the Apollo 11 samples came back, Neil Armstrong just jumped out, took a contingency sample just in case things went bad, stuck it in a sack, brought it back to Earth along with some other samples they collected. And this is an example of the kinds of very small rocks that were put in front of some of the scientists in the early days. Dr. John Wood of the Smithsonian was a well-known geologist, understood how planets work, and he noticed that in this basaltic collection of basaltic fragments, there were a very few white, pure anorthosite rocks that could not possibly be associated with the basalt where they were found. So they had to come from somewhere else through the impact process. He made a guess that they represented the lunar highlands very far away, which are also white, high albedo, might be small, and that implied that the lunar highlands might be this aluminum-rich anorthosite mineral. And he began thinking about the condensation sequence in the early nebula. When you start with a vapor and things cool down, the first thing to crystallize at the highest temperature are the aluminum plagioclase, feldspathic minerals. So he presumed that possibly something like this happened on the moon, and that implied, and we're starting to really kind of move along, that implied the moon must have been really melted in order for this kind of chemical precipitation to occur. And that led to the idea of what we call the magma ocean, that at the surface of the moon in the ancient history there was once a global ocean, and that the differentiation we see on the moon stems from that melting process. And this is still the kind of main paradigm in studying the moon, although there are lots of details now being put together that make the picture a little more complicated than this. But the immediate thing was, well, if this happened on the moon in the early stages, couldn't it happen on the Earth and the other planets? And people had never conceived of that before. So immediately you began to think that maybe the planets in their early history, heated by the accretional bombardment when they were first formed, were molten and formed magma oceans of the same kind that occurred on the moon. And that helped to unravel some of the not lesser understood properties of the relations of different minerals on the Earth. So by studying the moon, we immediately moved to an understanding of the history of the Earth, and we believe a history of the early Mars. Now, on the very surface of the moon, the material you see, it has the name regolith, which is a word that's created to mean a broken up lith, this rock, of broken rocks. And everything on the moon that you pick up has been broken off of something else, and probably lots of times. And there's now a general understanding of a process which we call comminution, which is breaking up, that starts from big rocks and goes into very fine-grained soils. The regolith is important partly because of when we go to the moon and operate there, we have to deal, that's what we deal with. That's the thing we get in the remote sensing. But when you go to other airless bodies, they too have regoliths. And so we try to understand what their surface properties are like through our understanding of the regolith on the moon. And the structure looks a little bit like this. We now find from the Grail spacecraft that orbited the moon took extraordinarily sensitive gravitational measurements. We know the moon is fractured to hundreds of kilometers. It's a mess. It's really hard to talk about it as being a solid object. Now, somehow some slides have gotten missing here, but I'm going to point out that the minerals on the moon are really quite simple because you don't have water, you don't have the clays, and because they're really simple, you can use remote sensing of reflectance of sunlight to tell you what minerals exist in what places. And once we have the samples and know what minerals are possible, we can start to make element maps around the moon. In addition, we have other tools. In this case, we're looking here at gamma rays that are emitted from the surface of the moon by impacts of cosmic rays onto the surface. And the gamma ray spectra show elements. They don't show minerals, they show elements. And then there's a neutron spectra, which also shows the amount of hydrogen. And there's an array of remote sensing techniques that work really well on the moon, have now been applied to Mars and Mercury. They don't work quite as well on Mars because there's an atmosphere and there are clays that complicate the mineralogy a great deal. But we now have the capability to make these maps with there's been a fleet of spacecraft, international spacecraft around the moon, Kagyu from Japan, Chandrayaan from India, the lunar reconnaissance orbiter of the United States, and for the first time after 35 years of almost no new data, we now have a lot of information. They're beginning to understand the geochemical structure. But we're still the question is, where did the moon actually come from? We know it's associated with the Earth, but why is there a moon with the Earth and not with a large moon associated with the other planets? And there were several hypotheses advanced of how it might happen. They all had problems in the physics. And finally, the one that was settled on was that very early, when the proto-Earth was being formed, a large body the size of Mars impacted the Earth with a glancing blow and threw out material. And through these kind of very sophisticated modeling using, as I say, computational fluid dynamics and huge supercomputer simulations, you can begin to match the properties of the Earth-Moon system. And one of the more intriguing properties we're beginning to understand from the lunar samples, from detailed study, is that the Earth and the Moon in their isotopic compositions are almost absolutely identical. That implies that the impact couldn't have been a lot different in its composition from the Earth and must have come from sort of nearby. It's a real kind of interesting puzzle that people are trying to go through. But one would think, well, come on, you're making this up. Well, it turns out there's actually just no other way to explain it. And even though it seems odd, it's not totally implausible in the early solar system where there are lots of planetary embryos being formed and they have to interact in pretty violent ways. In fact, I think one of the explanations for the very slow retrograde rotation of Venus is that a very large satellite came in and spiraled in and hit the surface and really slowed the rotation. But that's speculative. What I want to leave you with is that there's kind of a geologic story now that we can talk about of the moon and therefore apply to the other planets. We start out with the accretion of the object in the moon. It comes from the impact, but in the larger other terrestrial planets, it's part of the planetesimal accretion process that occurs in the early solar system. There is at some point, about 500 million years into the history of the solar system, a truly heavy bombardment of some kind, probably from the asteroid belt. And that forms the huge basins on the moon and creates what was called the lunar cataclysm. Subsequently, the moon, the heat thermal evolution of the moon allowed certain lavas to form subsurface and fill the basins that are on the near side, the side facing the Earth. And over the remaining billions of years, there was impact and regolith growth on the surface of the moon. So most of the evolution of the moon, where there's really planetary processes occurring, are only in the first 1 billion years of its 4.5 billion year history. So that's why the moon is so important in understanding the events in the very early solar system where we have absolutely no records on the Earth. So I'll just summarize by saying we know from the Apollo exploration that the moon is not primordial. It evolved in a planetary sense. It's truly ancient, preserves the early history. The youngest rocks are as old as the very oldest Earth rocks. The moon and the Earth are truly genetically related and formed from different portions of a common reservoir of materials. The moon is lifeless. It has no organic compounds. All the moon rocks came from high temperature processes with little or no involvement by water. Early in its history, the moon was melted to great depths in the magma ocean, and that magma ocean was, after it cooled, was followed by the series of huge asteroid impacts that created the basins. The moon's slightly asymmetrical, involved possibly as an influence of the evolution during the Earth's gravitational influence. And the surface of the moon is covered by this rubble pile, whose properties are really interesting and truly important to understand if we're going to have human exploration of the moon and other airless bodies. The scientific legacy of Apollo is that it established the moon as the keystone for understanding the solar system. Impacts are now an accepted geological process, and you now see newspaper articles all the time about when is the asteroid going to be hit, and shouldn't we be watching, and so on. There's newspaper articles when one passes between the Earth and the Moon. These kinds of things would never have been printed 20 years ago. Now there's a lot of interest in them. The study of the Moon actually created the field of planetary science. In the very first lunar science conferences, when they were reporting on the study of lunar samples, you had astronomers, you had chemists, you had geologists, you had physicists, and they all talked in their own tongue. And nobody could understand one another. It was a babel in a sense. But over a period of 3 or 4 years, they all learned each other's terminology and began to be comfortable with words that were not part of their root field and understand the context. And so that was where the field of planetary science was really born. And finally, what nobody realizes is there was, you do know there was a ton of money that was spent when Apollo project was going on. One of the investments was in laboratories and universities that could analyze infinitesimally small samples for the very first time. A geologist normally brings in a pile of rocks in the back of the pickup truck and looks at them in the lab. The lunar samples are handed out in milligram quantities. You need highly sophisticated instruments to A, measure them, and B, to understand what their context is in the larger sample you took them from. All of this is part of the legacy of the Apollo program. So, when you look at the moon and think about it, sure, it's an object where people who study the moon are really interested in it, but there are implications there for our understanding of the entire rest of the solar system. Thank you very much.
All right. Wendell will entertain some questions, and I'd like to start.
Oh,
if that's okay.
He knows the question I don't know. So this is a setup.
It's going to be about the dark side of the moon.
Yeah, that's the dark side of the moon.
No, it actually has to do with something that you talked about at the very end. You were there during the Apollo program. You worked with the astronauts.
Actually, that's all mythology. When you're a scientist, you don't get to work with the astronauts. Although, there were scientists in my group who trained the Apollo astronauts, and that is a really fascinating story. I'm sorry, I interrupted you.
No, it's okay.
A lot of people, they say, well, the astronauts were test pilots. They were sent to the moon. Come on, give me a break. They just picked up rocks. That's all they did. In fact, the engineers today, when we talk about going to the moon, say, well, how many rocks you want to pick up? And the other thing is, how many holes you want to drill? And that's all they think about is picking up rocks. Actually, the Harrison Schmitt was a trained geologist, but all of the others started out as test pilots. They were given thousands of hours of geologic training that is really not understood very well. Actually, now it's documented in a tome by Bill Finney. And some of them became very good field geologists. And I'll tell you one story. As the Apollo missions progressed, the scientific bodies got into huge fights over where we're going to go next in order to collect the new information that would tell us the most about the moon. And all the scientists had their favorite areas. In Apollo 16, when the Apollo 16 flight flew, they went to a place called the Descartes Highlands. And the reason they did was because the geologists said, this is a very unusual lava flow. This whole area has been covered with a massive flow, and we need to understand what kind of rocks these are, because they're different than the other lava flows on the moon. So they sent John Young to do this, and he was trained to look for the right kind of rocks. He got out and he looked around and he said, there aren't any basaltic rocks here. These rocks are all impact, they're breccias. And the geologist said, John, just do your job. Stop arguing. He said, no, the rocks you sent me for are not here. And they said, collect the rocks, shut up. So John went through and he argued with them all the way back to the Earth. And when they got back, John was right and the geologists were wrong. And the reason was because they were looking at the morphology of the area from photographs taken by spacecraft hundreds of kilometers away or 100 kilometers away, and it looked like them to lava flows, but it actually was a huge impact-related formation. And Dave Scott in 15 was a fantastic geologist. So those guys really contributed in real time to the scientific investigation of the moon in a very innovative and creative way, despite the fact they were just test pilots.
So that wasn't my question.
Oh, okay. Let's try again.
It really has to do with the fact that 40 some years have passed since Apollo, and you probably have the greatest perspective of anyone as to what the greatest gift of Apollo has been.
Well, I thought I just talked about it. There are actually two gifts. What from the science point of view, I've kind of gone into the things that we now know because of Apollo. But there is a second gift, and you guys, unfortunately, are a little young for this. But this guy is about the right age. It turns out that there were a whole generation of people around the world, not just United States citizens, but around the world, who saw the astronauts on the surface of the moon and thought that was just the coolest thing ever, and developed this idea that this was the first step in a process to move out into the solar system. And when the program was canceled about 1970 by President Nixon, of course the mission was carried on through 72, there was in many places among people who were inspired by that program a huge sense of betrayal, that the politicians didn't understand this, that for them it was just, we did it for this reason. John Logston has gone over that with you many times. But the people on the street had no sense that this was done as a political move, that it was something intrinsic in the human species of moving out there. And this inspiration has stayed with people, and it's kind of hidden. You don't see it in the newspapers until the 1990s and the dot-com revolution and the internet. That particular area created billionaires, and suddenly about 1999, 98, 99, these people with billions of dollars began doing what? Building rockets. Jeff Bezos, Blue Origin, Elon Musk, SpaceX, I'm trying to think of Paul Allen, and so on. You walk through these guys, they're doing things which prior to 1999 or 99 were done only by governments and space agencies. And these guys are doing it on their own because they have really deep pockets and they have a dream. And that dream came from the Apollo program. And I think the reason we have such a rich opportunity in the commercial sector today, when at least in the United States, the space agency's kind of going a little flat, is because of the inspiration of the Apollo program, which was never on the page as a reason to do it. But it's created a whole new kind of environment. And you guys are too young to have actually been there and felt that, but you are going to be the beneficiaries of the fact that these guys got really rich and were able to do something with their money to fulfill the dream that was instilled when they were really quite young.
Thanks.
I think we have some questions. Yes, questions?
I find it fascinating that there's knowledge occurred on the Apollo mission, like the impact craters, that I have always took for granted. I never thought they would be arguing about that. Moving forward, how can we get excited for going to Mars and find discoveries that we don't know yet? How can we get excited for things we don't know we're going to find?
Well, there are a lot of people excited about going to Mars. Jim Green's really excited about going to Mars, and he's old. And there are a lot of younger people who are really excited about going to Mars. They're generally excited about going to Mars. In fact, a large part of my career was spent in the 80s and the 90s debating with people like Bob Zubrin or Lou Friedman about, stop this moon stuff, let's go to Mars. And so at the AIAA meetings, the American Institute for Aeronautics and Astronautics, Aerospace Engineer Professional Society, I used to routinely get invited to give a paper in the same session that Lou Friedman was going to give a paper, because everybody liked to watch the blood. It was blood sport, you know. And I tended to be more philosophical. Lou Friedman tended to be more dogmatic. And I'll never forget. There was one session, and so I gave my paper. Yes, we're going to the moon, but this is the first step in a further exploration of the solar system. This is not just the moon for itself. And Lou Friedman was missing. Nobody knew where he was. And finally, as the session was ending, he came running in. His plane was late, and he had just been to a meeting of the American Conference of Bishops. And his big news was that the bishops had all voted to go to Mars. So it turns out to be largely a religious battle about going to the moon and Mars. And when you get down into people who are thinking about it in the hard technical terms, for human exploration, is what I'm talking about, that it turns out that the moon is a wonderful place to develop the technologies that are critical for understanding how to go to Mars. And I wrote a whole series of papers about this in the sort of 1998 to 2000, 2001 time frame on going to the moon and Mars. I stopped writing when President Bush 43 made the big vision for space exploration, because I thought, okay, done, don't have to worry about that anymore. And the argument is not that we are not going to go to Mars, it's that going to Mars right now is technically particularly difficult, particularly with respect to the human being. When people like you want to go to Mars, your first thing is just build a big rocket, build a big spaceship, put people in it. This is the Bob Zubrin talk. And we can go to Mars, not a problem. It's actually really, really difficult in terms of what happens to the human being themselves. If you don't care what happens to the crew, then yeah, we can do that. But if you really want people to thrive and succeed in a fashion where we can continue to move forward, you have a lot of learning to do, and I talk in these papers about that. Now, I think there is a report tomorrow night. John Logston and John Connolly are leading a discussion of the National Research Council report on the human space program, which just come out within the last few weeks. And it's going to say many of the things, I read the summary today, it's going to say many of the things that I talk about we need to go stepwise into this, partly because it's really expensive, partly because it's really dangerous, and partly because we've got to succeed at a series of levels before we, like the big rocket, and take off for the red planet. It's a much more complicated process than just building the world's biggest rocket. So your question was, how can we get excitement? And this is the question that we've, ever since I've been in the space program, it's how can we excite people? Well, a lot of people are excited, a lot of people are not excited. And people who really believe, who are believers, want to convince others. And I wrote a paper called Space Activism as an Epiphanetic Belief System. And what I did was compare what people who believe in space, and I'm not talking, this is not irrational, like they believe in the future. And my wife's very active in the Christian church, and I watched how the Christian church operates for people who believe in the Christian church and how they recruit. And I looked at how people who believe in space and how they recruit. And in the church, they go to talk to other people one-on-one and say, this is how it's changed my life, and I think you need to try to experience this. In the space business, they write a view graph with 6 bullets. Why we should go to space. Doesn't work. In this paper, I'm probably running out of time. But this paper, I was at a conference, I'd been thinking about this, and in 2003, I was at a conference in Hawaii about going to the moon, the International Lunar Exploration Working Group. Steve Durst was running the conference. In the afternoon, he said, Steve Durst, really nice guy, sort of mild-mannered. Okay, well, let's have a coffee break, and we'll continue in 20 minutes. So I grabbed the microphone from him, and I'm looking at these people. There's only about 50, 60 people here. We're in a hotel. We're sitting at tables, and by every place there's a little pad and a pencil, it says hotel, whatever. And I said, okay, look. I said, I want to do an experiment. Please bear with me. I said, I want to know how many of you developed your passion in space from some event in your life, some specific event in your life. And I want you to answer yes or no. And if the answer is yes, I want you to write down in your pad of paper, just very briefly, what that event was and how old you were. And so I ended up with 52 pieces of paper. Some of them with drawings on them, and some of them with that kind of stuff. Turns out that 80% of the people had a specific event that they remembered. And the reason I thought of this is because in my years of talking to people in space, they always said, oh, well, I was going to Girl Scout camp and I got a book out of the library and it was about space and I haven't stopped thinking about it since. Or there's always something. I was 5 years old, my dad said, come down and watch the astronauts on the moon, and that was it. 80% said yes, they had something. Of the other 20%, almost everybody who said no actually told me a story anyway. And there were only 2 people in the room whose answer was, I just happened to get a job and I was in the right place at the right time. One of those people was me. And the other person was astronaut John Young. Everybody else in the room had a story. And I wrote a paper about it with examples, some examples of things I got back from people. And my point of this was, people are passionate about space because they've had some specific experience that triggered that passion. And it's true in almost anything in life. That's where you find it. And if we want people to be excited about space, we need to find ways where those people can actually get intimately involved in what we do in space. It's not the domain of a professor and his graduate students, or a mission controller, or an astronaut. It has to be ways that all of us can get involved. And you see things like Galaxy Zoo or Moon Zoo, or where people are doing group research on massive databases and so on. And that's a step forward. But we need to have ways that people actually find in their own lives that I'm part of it. And that's what the space program lacks, because it's always an elite few who get to do cool stuff.
Hi, my question is about the future of the moon. In regard with all this story about asteroid mining, do you think the moon could be in the next decade like the new El Dorado of the Earth for nations allowed to access the moon and extract all the resources?
That's an interesting question. I talked about in 1982, started beginning this idea of advocating. And one of the first things I found within a couple of years was exactly that. We're going to use the moon for resources. And I happened to be at Los Alamos, and I was with a colleague that we were working on these things together. And he said, I want you to meet this guy down the hall. He's a Nobel Prize winning chemist. And I want you to talk to him about going to the moon, because if you can get him on our side. So I went down the hall, and he's a really nice guy, so I explained all this to him. He looked at me and he said, if we start running out of stuff, we are going to mine beach sand on the Earth before we ever go to the moon and start digging up dirt there. And I thought, oh. And then I began to read, and I found out, for example, when Zaire, remember there was a country called Zaire at one time, and I don't know what it's called now, the Congo, and it had rare earth metals, and it went, and suddenly the supply of these precious metals dried up, and the military needed them. They started mining dumps for toasters because they had a lot of this elements in them. I just saw an article in the Airplane magazine coming here about fracking because we're running out of oil, there's no more oil, and suddenly this new technique is discovered and the technology has changed, and suddenly the U.S. might become a net exporter of oil. And the problem is, and this colleague of mine at Los Alamos told me this many, many years ago, is that there was a club of Rome that said we're going to run out of resources and then civilization is going to collapse. Julian Simon, who is a well-known economist, had an alternate explanation that when people really get run out of things, they adapt and use something else or find a new way to do things, because humans are so incredibly technological. They can find ways and technology to do things that we thought we were going to run out of, and the information revolution in a more abstract sense is an example of this. So if you talk about we're going to the moon for resources, it gets very difficult to put together that scenario because there are so many alternative approaches and technologies you and I don't know about, and suddenly, oh wow, look at that. Now, if we go into space, it's a different question, because it's so expensive in the current paradigm to take things from here to the colonists that they need to learn to live off the land, as John Conlon and I often talked about, in situ resource utilization. You may have heard that term. I was one of the two people who invented it. Not sure if it's a good idea. But ISRU, you need to live off the land and get rid of the import, and then you become less dependent. And there's been a lot of science fiction books written about that. So that's where, to me, is where the resource is going to come in from extraterrestrial, is once we have a space economy. And that's one of the things I kept looking for, is when is the space economy going to occur? When are we going to have something created in space that services something else in space? The beginnings of an actual economy in space and not dependent on import from the Earth. And there are some things starting to happen. So.
Any others?
Hi, I just want to ask about helium-3. What is the hyper-reality behind that? Off the top of it.
Well, I was one of the people who received the original letter from Jerry Kolsinski, who is a fusion scientist at the University of Wisconsin. And he and his colleagues were big advocates of building fusion reactors using helium-3. And the reason was that the reaction involving helium-3 generates only protons and not neutrons. And so you could capture the energy from protons. When you can't capture the energy from neutrons, neutrons hit the wall of your reactor and cause it to degrade over time. And so you would like a reaction that has only protons. But the helium-3 reaction is really difficult to sustain, much more difficult than the deuterium reaction. But the other thing was that there's not much helium-3 on Earth. And the question that they were raising was, in this future scenario where we're going to win, and build those reactors, where's the helium-3 going to come from? And they thought about the atmosphere of Jupiter. And then they read in the paper that scientists had discovered helium in lunar samples. So they sent a letter saying, you know, well, what is this? And it became a huge deal. Jack Schmidt still talks about it. He was up at Wisconsin with those guys for a while. The reality is that you've got that mining helium-3 is feasible at the view graph level, and with a huge investment and some technical innovation could be done probably in a 30, 50-year time frame. And then there's who's the customer. And when you go to the fusion reaction community, fusion itself is always 10 to 20 years away, and helium-3 fusion is a little further away than that. So I pointed out to this director of the Johnson Space Center some decades ago that, yeah, it's possible, and it's interesting, the two technologies merge around 2050. So, possibly. But that, right now, it's kind of a red herring. Now, I'm embarrassed to say that because there are people from major space agencies probably sitting in this room who are having money spent inside their agencies based in some extent on a belief that this is going to be a reality. And I just have to place myself in the area of the skeptic about the reality. I mean, it's not impossible. It's just there are too many things.
Do a couple more. We'll shoot for 8. Okay.
Wendell, could you say something about water on the moon?
I say something about it. Yeah, that's really interesting. That's really interesting. I wish. Well, okay, I will say something.
Which I hadn't asked?
No. It's a good question, and I'm just embarrassed that I can't give you a really detailed scientific answer. So what I'm going to tell you is this: when the first lunar samples were examined, all of the chemical reactions, the iron in all the lunar samples, for example, is ferrous iron, not ferric like on the Earth, and that meant that there was just no oxygen around and presumably no water around. And so the geologists came to the conclusion that when these magmas were formed, they were without water. And when we say without water, it's not exactly zero, but it's very, very tiny quantities. So there has been this kind of law or dogma throughout the history of lunar science up until very recently, that there just wasn't much, there was so little water that you neglected when you built your models and so on. Alberto Sal looked at some lunar glasses that were collected by Jack Schmidt in the Apollo 17 mission. These glasses are little round, when you look at them, they're little beautifully colored beads. They are created in volcanic fire fountains, where the molten material is thrown up, and as it cools radiatively while it's flying through space, it forms little balls. And it turns out that these things collect and entrap whatever gases are around at the time. So he now has equipment, and once again, this is a story of evolving capability in analytical labs. More and more detailed investigations are possible. This is an important story. And he was able to measure very tiny quantities in these glass beads, and through a series of modeling exercises, infer that the water that was in the original stuff that popped up was actually substantial. You're not talking potions, but you're talking more than zero. And his work was so good and so thorough that people said, whoa, we got to look at this. And people now begin looking at it. They look at particular minerals containing phosphates called apatites, and they're analyzing, trying to understand exactly what is the water story. But the water story, of course, is a big news item, but people like this place, water on the moon, oh my God, now we can go there. No, it's not exactly that. It's still very tiny amounts, but suddenly, when you do your models of how the magma is generated, you have to allow for the possibility that there was a little bit of water there that changes the chemical reactions in the magma and can change it in fairly substantial ways. So, and then the second story, of course, is the Chandrayaan epoxy. And what was the third spacecraft that flew by the moon? Roger Clark wrote a paper. There were these 3 papers that appeared in Science, and it turns out that a remote sensing experiment with Carly Peters, principal investigator at Brown University, was on the Indian Chandrayaan experiment, and was able to just partially see at the end of their capability a portion of an absorption band that's related to water or hydroxyls. And they noticed this band had different depths on the moon from the surface, very faint, that changed with the fact of whether it was noon, very hot, or night, well, you can't look at night, or terminator, where it's cool. And then they got some people who'd been on spacecraft that had flown by the moon and taken infrared, but not in the orbiting sense, they'd done a pass-by. And they saw some of these bands, and they came to the conclusion that the lunar surface seems to have an accumulation of water in a monomolecular layer. I'm talking about one atom deep. And that this comes after dawn from the condensation and then evaporates over noon and is more prominent at the poles where it's always kind of cool. And so people have kind of built stories around this. The more we study it, the more complicated it gets. And part of it is due to the fact that we don't have the right kinds of equipment to really measure it correctly. So that's my version of the water story.
One more question.
So this is specifically moon related, but you hinted at interesting developments in developing an economy in space. What do you think it is that will draw us out into space? I mean, it seems to me something has to be returned to Earth of value to create interest in space. Is there something that you see is going to do that for us in the future?
Well, right now, information is coming from space. So we have an internet revolution, and a lot of that information flow and remote sensing and so on is coming from space. So there are, what's the unit of information? Yeah, it's like a photon, or whatever. You get photons up there, and you send back bytes or bits to the Earth, and this data, this collection of ones and zeros, is organized in a way, right? So something is coming from space. The economy really comes when there is something. The space economy really comes when there's something. And I'll just go one more step. On the space station, they asked the same question. And one of the answers in the brochures in the space station is that drug companies were going to make special drugs in space that you couldn't make here. They're really, 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 really expensive. They're just sick. And that these things would be a product. It hasn't exactly worked that way, but there's been some success. So you're looking at things that are, quote, manufactured in space that have extraordinarily high value per unit mass on the Earth. And by the way, if there was gold bars sitting on the moon, it wouldn't make money to bring them to Earth. You lose money. So the real question in space is, you're in space where you're spending a lot of money to be there and to get there. If you can reduce your cost by utilizing something that's there or a service that exists there, then you're going to do that as opposed to getting the thing from, that's expensive import. So that's what I was alluding to about the beginnings of a space economy. And now we're talking about people who might be sending up spacecraft that refurbish satellites or refuel satellites that weren't designed to be refueled. And there's talk about that. Something like that is sort of the beginnings.
I thought at one of the beginnings in the early days when I'm trying to rack my brain what could possibly be is policing. There's an international telecommunications union that has a lot of very important meetings that go over the geostationary satellite constellations and make sure that the frequency of satellite A doesn't interfere with the frequency of satellite F or cross over into its path. But lately there have been some things happening, and they all fulminate and get really mad, but there's nobody up there moving it back or whatever. So, but once you have a quote police force, then you're immediately in a political question about, well, who's in charge of the police force? And it gets really, really complicated. So those are the parameters that I'm kind of searching for when I talk about an economy in space, or the first hints of that, kind of selling something in space to something else in space. Thank you very much. I appreciate it.
Thank you, Wendell. For most of my career, I had the honor of spending an hour every Thursday morning with Wendell and a bunch of other scientists and engineers talking much like we were talking tonight. You'll get a bit of that experience at a cocktail party we have organized just outside, where hopefully we can continue this conversation. So thank you all for coming. I'd like to thank ETS and HTC for sponsoring our cocktail party tonight and for sponsoring this talk. And let's go out and talk some space philosophy.